Welcome to True Projects. In this video, we are going to explain about the project title Multi-Level Residual Feature Fusion Network for Thoracic Disease Classification in Chest X-ray Images. Introduction. The project centers around developing a system that can automatically detect thoracic disease by analyzing chest X-ray CXI images. The goal is to create a computer-aided diagnosis tool to assist in identifying these diseases. Traditional diagnostic methods for thoracic disease typically involve manual analysis trained by medical professionals. This process is time consuming and requires laborious manual labeling of X ray images by doctors. Deep learning, particularly convolutional neural networks (CNNs), has emerged as a promising approach for medical image analysis. CNNs excel at recognizing patterns in images and have shown great potential in various medical applications, including analyzing X ray images for disease identification. The existing CNN based methods for classifying thoracic disease fall into three main categories: network structure optimization, enhancing the architecture and design of neural networks; attention guided methods, using mechanism to focus on specific regions of features within the images; correlation modeling methods, analyzing relationships and correlations between different elements in the images. Despite the advancements, the existing CNN-based methods have shortcomings. They struggle with capturing information at multiple scales and effectively leveraging the meaning or context present at various stages of image downsampling. To address these limitations, the project proposes a novel approach called the Multi-Level Residual Feature Fusion Network. This new architecture aims to overcome the shortcomings of existing methods by improving the fusion of features extracted at different levels of the network, thereby enabling better utilization of multi-scale and semantic information. The claim is that this proposed method outperforms existing state-of-the-art techniques in the automated identification of thoracic disease from CXI images. Objective: the main goal of this project is to create a multi-level residual feature fusion network. This network architecture is specifically designed for the classification of thoracic disease using chest X-ray images. The main aim is to develop a model that can effectively identify various thoracic disease from these medical images. The existing methods used for classifying thoracic disease from chest X-ray images have shortcomings. They struggle with extracting features at multiple scales and accurately pinpointing the spatial locations of lesions or abnormalities within the images. The multi-level residual feature fusion network is designed to address existing limitations by incorporating a feature extractor to capture multi-scale semantic information and a multi-level residual feature classifier to refine disease-specific features at precise spatial locations within chest X-ray images. The network incorporates ECA, efficient channel attention modules, to emphasize critical pathological information present in the chest X-ray images. These attention mechanisms help the network focus more effectively on the most relevant features, improving the accuracy of disease classification. The performance of MLRF-net is assessed using two datasets, chest X-ray 14 and TechSpert. These datasets are commonly used in medical imaging research. The evaluation involves comparing MLRF-net's performance with existing state-of-the-art methods to gauge its effectiveness and superiority. The overarching objective is to achieve better classification performance. Additionally, the project aims to explore the relationship or interdependencies among different labels for thoracic disease. It also aims to investigate techniques for compressing the model, making it more efficient without compromising its accuracy. This points towards the continued development and enhancement of MLRF-net and related methodologies for thoracic disease classification. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are: application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, Front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. It involves importing necessary libraries and packages in the programming environment to support the project's implementation. These packages include deep learning frameworks like TensorFlow or PyTorch, data manipulation tools such as Pandas and NumPy, image processing libraries like OpenCV, and other utilities required for data handling, model creation, and analysis. Exploring the dataset. CheckSpurt and Chest X-ray 14. These datasets consist of chest X-ray images along with labels or annotations for different thoracic diseases. This phase involves loading, inspecting, and understanding the structure of the datasets. Exploratory data analysis (EDA) is performed to comprehend the distribution of images, labels, any missing values, and other relevant attributes. This exploration assists in preparing the data for model training. Image processing using image data generator. This is a tool in libraries like Keras that facilitates on the fly data augmentation during model training. Rescaling the image. Adjust pixel values to a specific range, often between 0 and 1 for normalization. Shear transformation. Applies a shearing effect to images, distorting them along an axis to introduce variations. Zooming the image. Alters the scale of the image to create different perspectives for model learning. Horizontal flip. Generates mirrored images horizontally, enhancing the dataset's diversity. Reshaping the image. Adjust the dimensions of images to fit the model's input requirements, ensuring uniformity across the dataset. Building the model. This phase involves creating the architecture of the neural network model specifically designed for thoracic disease classification from chest X-ray images, determining the layers and the configurations, defining activation functions, and any additional components like residual connections or attention mechanism, compiling the model with appropriate optimizers, loss functions, and evaluation metrics, training the model using the prepared dataset and evaluating its performance for disease classification. Training the model. This phase involves teaching the multi-level residual feature fusion network using a large dataset of chest X-ray images. The model learns to recognize complex patterns and features indicative of various thoracic disease by adjusting its parameters during numerous iterations. Flask framework with SQLite for sign up and sign in. Utilizes Flask, a web framework in Python, and SQLite, a lightweight relational database, to create a user authentication system. Enables users to create accounts, sign up securely, log in, sign in, and manage their authentication credentials for accessing the application. User upload an image for analysis. Provides a user-friendly interface allowing individuals to upload chest X-ray images via the web application. Allows users to submit the images for analysis by the trained model. The given input is pre-processed. Standardizes the user-uploaded images by applying the same pre-processing steps used during model training. This ensures consistency in image format and characteristics required by the trained model. The trained model is used for predicting the result. Employs the trained multi-level residual feature fusion network to process the pre-processed image. The model applies learned patterns and features to predict the presence or absence of thoracic disease in the submitted X-ray image. Final outcome is displayed through front end. Communicates the model's analysis or prediction outcomes effectively on the web application's interface. Presents the predicted disease classification in a user-friendly format, aiding users in comprehending the model's analysis of the chest X-ray images they uploaded. Algorithms used. To implement this project, we have utilized the following algorithms. The first algorithm is ResNet 50. ResNet 50 is a variant of the ResNet architecture featuring 50 layers. It employs residual connections that enable the flow of gradients effectively during training, mitigating the vanishing gradient problem. ResNet 50 serves as the backbone or base architecture for feature extraction in the multi-level residual feature fusion network. Its depth and skip connections allow for effective extraction of features from chest X-ray images, aiding in thoracic disease classification. DenseNet 121. DenseNet 121 is characterized by densely connected layers. Dense connections facilitate each layer receiving input from all preceding layers, promoting extensive feature reuse and information flow. DenseNet 121 is utilized as the backbone of feature extractor within the multi-level residual feature fusion network. Its dense connectivity enables the network to capture fine-grained features and relationships within chest X-ray images, potentially improving disease classification accuracy. MLR FNet PyTorch Backbone ResNet. The multi-level residual feature fusion network employs a PyTorch-based ResNet as its backbone. MLRFNet integrates a multi-level residual feature fusion mechanism derived from ResNet architecture, enhancing feature learning across multiple levels. MLRFNet serves as the primary architecture specifically designed for thoracic disease classification in chest X-ray images. Its integration of a ResNet backbone enables the network to capture multi-level features and fuse residual features effectively, potentially enhancing disease classification accuracy. As an extension, we applied an ensemble method that combines the predictions of multiple individual models to produce a more robust and accurate final prediction. Comparison graphs. Comparison graphs offer a visual breakdown of how a model performs across essential evaluation metrics. Models are compared with the parameters accuracy, precision, recall, and FN score. This is the accuracy comparison graph. On the x-axis, we have accuracy score, and on the y-axis, we have algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positive and true negative, to the total number of instances. This is the precision comparison graph. On the x-axis, we have precision score, and on the y-axis, we have algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is the recall comparison graph. On the x-axis, we have recall score, and on the y-axis, we have algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. On the x-axis, we have FN score, and on the y-axis, we have algorithm name. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. The algorithm, which is performing best in all the performance metric, will be used for prediction. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is model file, which contains algorithm information which will be loaded into the project code during runtime. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. Here, I'm copying the path. Now open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flash framework will host the application locally at the default address, localhost, which is this, and port, which is this. Now copy this local link provided by the Flash framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flash framework. If we are a new user, we need to register first. So click on sign up button here. So here we need to enter all these details to register. But I have already registered. So click on sign in link here. So here we need to enter the username and the password which we have registered. And then click on login. We have logged in successfully. So here we need to upload the image to classify the thoracic disease in chest X-ray images. Click on choose file, select the image, click on open. Now click on upload button. This is the uploaded image and it is predicted as the patient is normal. Now click on try again to upload some more images. Click on choose file, select the image. This is the uploaded image and it is predicted as the patient is diagnosed with pneumonia. Let us upload some more images. Click on upload button. This is the uploaded image and it is predicted as the patient is diagnosed with COVID-19. In this way, by uploading the image, we can predict whether the person is having thoracic disease or not. Now click on sign out button here. Conclusion. The multi-level residual feature fusion network MLRFnet outperformed existing state-of-the-art methods in classifying thoracic disease from chest X-ray images. This indicates that MLRFnet architecture has shown superior performance compared to existing methods, suggesting its effectiveness in accurately identifying and classifying thoracic diseases. MLRFnet integrated a feature extractor and a multi-level residual feature classifier. This architecture enabled the network to capture multi-scale features, understanding information across different levels of granularity, and accurately locate lesions spatially within the chest X-ray images. MLRFnet's experiments showcased improved disease recognition by retaining low-level features such as spatial positioning and texture of lesions. Preserving these detailed features indicates the network's ability to understand critical aspects of diseases, potentially enhancing its diagnostic accuracy. Future efforts will concentrate on exploring relationships between different thoracic disease labels. This exploration aims to understand how these diseases correlate or influence each other within the context of chest X-ray images. Additionally, there will be an investigation into methods for compressing the MLRFnet model, making it more efficient without compromising its performance. Model compression is vital for deploying models in resource-constrained environments.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.